Our next speaker, also from the Max Planck Institutes, is Nihat Ay, who is a professor at the Max Planck Institute for Mathematics in the Sciences. Nihat, the floor is all yours.
Great conference and for giving me the opportunity to talk here. So as Metin already highlighted, maybe the core component, reoccurring component within our field is the sensory motor loop. That's the thing we all agree on. This is the causal diagram of the sensory motor loop, which highlights, so to say, unfolded in time, the interaction between the world, denoted by W, and the brain state, the controller state, denoted by C. And the interaction is mediated through sensing and acting. So that's the basic structure. And we all know, as a result of this, we get behavior, and behavior is taking place in the world. So that's, so to say, part of the world. I always consider the body as being part of the world. So we have to distinguish several kinds of mechanisms. So as you see in the sensory motor loop, we have several mechanisms denoted by alpha, beta, phi, and pi. So alpha and beta define mathematically the embodiment constraints. So alpha is the physical process, if you wish, in the context of actuator states, and beta is the sensory mechanism. So altogether, alpha and beta, I use the shorthand notation sigma in order to denote the embodiment constraints. And in addition to these exogenous mechanisms, we have endogenous mechanisms, namely the control mechanisms, which are phi and pi. Pi is the policy, and phi describes the internal dynamics of the brain, so to say. And a recurrent idea is this idea of optimal coupling. So we talk, for example, about co-evolution or co-design. So there's this idea that we can achieve desired behavioral patterns in terms of optimally coupling the embodiment constraints with the control mechanisms. And here, because of the core phenomenon is that we can achieve highly complex behavioral patterns with very cheap and simple control mechanisms. That's the core idea of cheap control. So basically, the physics and the constraints take part of the complexity of generating the complexity that we see in the behavior space. And I want to maybe not challenge, but extend this idea a little bit. So this optimal coupling is, of course, assuming that the embodiment constraints remain the same. But that's not the case. We have, of course, through growth, development, and aging, the embodiment is changing all the time. So our brain needs some ability to adjust to the embodiment constraints. So a control mechanism, which is optimal for one body, it might not be optimal for the same body at a later time point. But we also have more drastic changes of embodiment constraints, for example, through diseases or limb loss. In that case, of course, we cannot, the brain cannot adjust to this new situation completely, but there should be some ability to readjust and regain some functionality. So let's try to put it in some kind of pre-formal way. So we have these two axes here. The x-axis stands for the embodiment constraints. Here we have sigma 0 and the given embodiment constraints, and the y-axis is the control mechanism. And we have this optimal coupling, sigma 0 and gamma 0. This is the coupling that I talked about previously. But we can also highlight all kinds of optimal couplings denoted by this line here. And let's say there is some change in the embodiment constraints. We move from sigma 0 to sigma 1. So what does this mean? The pair in this XY diagram, the point consisting of of these two coordinates will move to this point here. And suddenly it's not anymore on this optimal coupling line. So we have to readjust by moving up again until we meet that optimality manifold again. So that corresponds, of course, to a change of the control mechanism. This is just the formal way to say that the brain has to readjust to the changes in the embodiment. But what does that mean? That means the following. If we have some space of variability, possible changes of the embodiment constraints, that has to be matched by corresponding changes in the control mechanisms. And so I formulated this in this way. The variability of the embodiment constraints has to be matched by the corresponding variability of the brain in order to learn new control mechanisms if necessitated by perturbations. In other words, the complexity of the brain has to match the complexity of perturbations in the embodiment constraints. And with complexity, I don't mean here, it's more like a dimension complexity. So the dimensionality of the perturbations should be matched by the dimensionality of the mechanisms that can be generated by the brain. So what does this mean? It means that if we have a neural network that is capable of generating gamma zero, let's say, that will not be able, generically not be able to generate all other mechanisms that are required for compensating perturbations. So that means a cheap control that we had in the previous setting, where we have this optimal coupling sigma zero and gamma zero, will not be enough anymore. So the system has to be enlarged and it has to be equipped with a learning algorithm to compensate perturbations. So that's my first argument, to actually not to have the cheapest design. The second argument is the following. It refers to perturbations, intrinsic perturbations. So not just the body is changing. Let's say you have some structural perturbations, internal perturbations of the brain itself. So almost by definition, if the architecture was minimal and you remove some part, it will not be able to recover the original function anymore. So that's, so to say, a robustness argument. So you need some robustness mechanisms which involve redundancy and duplication operations. So this is a second argument in order to not to work with the smallest architecture that might be possible, which we always consider. And let me come to the last argument. It's about prediction. So until now, up to now, I have talked about external and internal perturbations, which all refer to the policy pi. But as we have heard many times today, that just acting is not enough. You have to be able to predict the outcome of your actions. So that's the prediction mechanism. And that's very interesting, actually. Even if pi is very simple, let's forget about the perturbations. Let's say it's really cheap. In order to predict the outcome of your actions, it can be very hard, because the outcome of your actions involves alpha and beta, the embodiment mechanisms itself, which we assume to be very complex. So even if the control can be achieved in order to generate complex behavior, the prediction of the outcome of that control will be very hard. Coming back maybe, or referring to Andy Clark's comment, maybe that we don't have to predict everything, full prediction, but only those aspects that are important for us in order to perform particular behaviors. So why is prediction required? One argument could be in order to have actually deliberative actions. So we have an intention map, and then we have a deliberative action in order to achieve our goals. And we are studying this in the context of actually within a DFG priority program, the active self. And let me summarize. So I have provided arguments for not going with the cheapest architecture, and those arguments were adaptation to changes of the embodiment, adaptation to internal structural perturbations, and incorporation of predictive processes. Let me relate this to two aspects studied in machine learning. In machine learning, you have this universal approximation property. I think this is not required at all. You don't want to represent all possible functions. But there's this notion of over-parameterization, which is becoming more and more important. And there are works showing that in over-parameterized systems, learning is improved. So that might be something also relevant within our field. This is my last slide. I just want to mention that I'm currently building up a new institute at the Hamburg University of Technology, the Institute of Data Science Foundations, which will be located at the Hamburg Innovation Port. That's something not existing yet. It's under construction. And I'm currently looking for a postdoc who is strong in mathematics and interested in robotics.